the great choice of matrix. That's the choice a physicist would do when he or she had to finally bring coordinates in unwillingly. The coordinates to be chosen, the good coordinates, are the eigenvectors. Because if I did this projection in the standard basis, which I could do, right? I could do the whole thing in the standard basis. Let me better try if I can do that. What are we calling that? So I'll have to tell you now which line we're projecting on. Say the 45-degree line. So say we're projecting onto 45-degree line, and we use not the eigenvector basis, but the standard basis. The standard basis, V1 is 1, 0, and V2 is 0, 1. And again, I'll use the same basis for the outputs. Then I have to do this. I can find a matrix. It'll be the matrix that we would always think of. It would be the projection matrix. It's the matrix that we learned about in Chapter 4. It's what I call the matrix. The matrix is, do you remember P was A transpose over A transpose A? And I think in this example, it'll come out 1/2, 1/2, 1/2, 1/2. I believe that's the matrix that comes from our formula. And that's the matrix that'll do the job. If I give you the input, if I give you this input, 1, 0, what's the output? The output is 1/2, 1/2. And that should be the right projection. And if I give you the input 0, 1, the output is again 1/2, 1/2. Again, the projection. So that's the matrix, but not diagonal, of course. Because we didn't choose a great basis, we just chose the handiest basis. Well, so the whole course has practically been about the handiest basis and just dealing with the matrix that we got. And it's not that bad a matrix. It's symmetric, and it has this p squared equal p property. All those things are good. But in the best basis, it's easy to see that p squared equals p, and it's symmetric, and it's diagonal. So that's the idea then is, do you see now how I'm associating a matrix to the transformation? I better write the rule down. The rule to find the matrix, A. All right, first column. So, rule to find A. We're given the bases. Of course, there's no way we could construct the matrix until we're told what the bases are. So we're given the input basis and the output basis, V1 to Vn, W1 to Wm. Those are given. Now, in the first column of A, how do I find that column? The first column of the matrix. So that should tell me what happens to the first basis vector. So the rule is apply the linear transformation to V1, to the first basis vector. And then I'll write it. So that's the output, right? The input is V1. What's the output? The output is in the output space. It's some combination of these guys. And it's that combination that goes into the first column. So I'll put this word right. So I'll say it in words again. How to find this matrix. Take the first basis vector. Apply the transformation. Then it's in the output space, T of V1. So it's some combination of these outputs, this output basis. So that combination, the coefficients in that combination will be the first column. So A1, A row 2, column 1, W2, A M1 Wm. There are the numbers in the first column of the matrix. Second column. Let me make the point by doing the second column. Second column of A. What's the idea now? I take the second basis vector, I apply the transformation to it. Now I got an output, so it's some combination in the output basis, and that combination is the bunch of numbers that should go in the second column of the matrix. Okay. And so forth. So I get a matrix. And the matrix I get does the right job. Now, the matrix constructed that way, and following the rules of matrix multiplication, the result will be that if I give you the input coordinates and I multiply by the matrix, so the outcome of all this is A times the input coordinates correctly reproduces the output coordinates. Why is this right? Let me just check the first column. Suppose the input coordinates are 1 and all zeros. What does that mean? What's the input? If the input coordinates are 1 and the rest zeros, then the input is V1, right? That's the vector that has coordinates 1 and all zeros. Okay? When I multiply A by the 1 and all zeros, I'll get the first column of A. I'll get these numbers. And sure enough, those are the output coordinates for T of V1. So we made it right on the first column. We made it right on the second column. We made it right on all the basis vectors. And then it has to be right on every vector. Okay. So there is a picture of the matrix for a linear transformation. Finally, let me give you a different linear transformation. The linear transformation that takes the derivative. That's a linear transformation. Suppose the input space is all combinations C1 plus C2x plus C3x squared. So the basis is these simple functions. Then what's the output? Is the derivative. The output is the derivative. So the output is C2 plus 2C3x. And let's take as output basis the vectors 1 and x. So we're going from a three-dimensional space of inputs to a two-dimensional space of outputs by the derivative. And I don't know if you ever thought that the derivative is linear. But if it weren't linear, taking derivatives would take forever, right? We are able to compute derivatives of functions exactly because we know it's a linear transformation. So that if we learn the derivatives of a few functions like sine x and cos x and e to the x and another little short list, then we can take all their combinations and we can do all the derivatives. Okay, now what's the matrix? What's the matrix? So I want the matrix to multiply these input vectors, input coordinates, and give these output coordinates. So I just think, okay, what's the matrix that does it? I can follow my rule of construction, or I can see what the matrix is. It should be a 2 by 3 matrix, right? And the matrix, so I'm just figuring out, what do I want? Let me write it here. What do I want for my matrix? What should that matrix do? Well, I want to get C2 in the first output, so 0, 1, 0 will do it. I want to get 2C3, so 0, 0, 2 will do it. That's the matrix for this linear transformation with those bases and those coordinates. You see, it just clicks. And the whole point is that the inverse matrix gives the inverse to the linear transformation, that the product of two matrices gives the right matrix for the product of two transformations. Matrix multiplication really came from linear transformations. I better pick up on that theme Monday after Thanksgiving. And I hope you have a great holiday. I hope Indian summer keeps going. Okay, see you on Monday.